Chapter 1b, Review of Electrochemistry. The content of this chapter is taken from Chapter 17 of Freshman Chemistry textbook, written by McMurray and Fay. In the Chapter 1a, as the previous class was treating the basics of electrochemistry. Also in this Chapter 1b, I'd like to introduce some basics of electrochemistry again by reviewing the freshman chemistry textbook. Here is the reduction potential. You have learned about that in the previous class. So here is a big table of reduction potentials. The title of this table is Standard Reduction Potentials at 25 Celsius degree, and here are various reduction half reaction, and also the reduction potential value are listed on the next column. I'd like to make several points about the reduction potential. The first point is about the reduction. I mean, the reaction is based on the reduction, not the oxidation. So on this reduction process, we have defined the values of the potential. So it is called reduction potential. Here is an example. Copper 2 plus 2 electron is going to copper. Definitely this is the reduction, and its reduction potential was obtained at plus 0.34 volt. This value is about the reduction, not the oxidation by definition. So here is the question. What is the potential of the copper oxidation? I mean, what is the potential of the Bergold reaction of this electrochemistry? Some of you guys would say, okay, the answer is minus 0.34. Plus 0.34 volt is obtained at the reduction process, and the copper oxidation is the Bergold reaction of the reduction process, so we should put negative sign on the 0.34 volt. So the answer is minus 0.34 volt about the copper reduction to copper 2 plus. Is it right? I can say it is wrong. The correct answer is the potential of the copper oxidation, which is the Bergold reaction of the reduction process, is the same value at plus 0.34 volt. Why? I'd like to say about the phase transition from liquid to gas or gas to liquid of water. So here is the temperature 100 Celsius degree. As you know, this is the boiling point of water. So under the 100 Celsius degree, we have a liquid water. Liquid. Above 100 Celsius degree, we would have a gas phase water there. And the boiling point is 100 Celsius degree. It means the phase transition from liquid to gas, upward direction. So my question is that what is the condensation temperature from gas to liquid? Is it minus 100 Celsius degree? No. It should be plus 100 Celsius degree. Actually, at 100 Celsius degree, there is an equilibrium between gas phase and liquid phase. That is to say, gas and liquid phases are coexistent at this temperature. So at 100 Celsius degree, we have Ford reaction from liquid to gas, also Backward reaction from gas to liquid. So let's go back to the reduction potential. At plus 0.34 volt, what happens? Copper 2 plus is going to copper, and also copper is going to copper 2 plus. There is an equilibrium between copper 2 plus and copper metal. If you applied more, for example, if you applied some plus 0.5 volt at this system, then the copper metal is going back to copper 2 plus, because more positive potential indicates more oxidative environment into the system. Let's go to the other way. So right now I'd like to apply plus 0.1 volt, which is much more negative than the plus 0.34 volt. So what happens? Then right now we are on the more reductive environment. So copper 2 plus is going to copper. However, at 0.34 volt, there is an equilibrium between copper 2 plus and copper. Actually, at this situation, you would have one molarity of copper 2 plus and one molarity of copper metal there. So, the reduction potential can be considered as the oxidation potential also. So sometimes it is called electrochemical potential. Sometimes it is called redox potential, including oxidation and reduction. Redox potential. REDOX. That is the first point of the reduction potential. And let's go to the title of this table. Let me change the pointer to pen. No, pen to pointer. And then the title of this table is Standard Reduction Potentials at 25 Celsius degree. There are two specific conditions of the reduction potential listed in this table. The first one is standard. Standard indicates a specific concentration of copper 2 plus and copper. The other thing is the temperature. The temperature is at 25 Celsius degree. Even if I have said, okay, here is some reduction potential of those various electrochemistry, but it is not true. This value is not the reduction potential. This value is standard reduction potentials at 25 Celsius degree. What is the meaning of standard? Standard means standard state. The standard state is a kind of a reference point at which the activities of species are 1. It means copper 2 plus is 1 molarity and copper is 1 molarity. Activity is a kind of concentration. Actually, it is an effective concentration. So one activity indicates around 1 molarity concentration. Actually, it is not exactly 1 molarity, but around the 1 molarity. So standard reduction potential is the reduction potential at activity is equal to 1. So this value is not the reduction potential, but the standard reduction potential. If you change it, the concentration of copper 2 plus from 1 molarity to 0.1 molarity, this value is changing. So you can expect the value at 0.1 molarity by using Nernst equation, but it is not the standard reduction potential. The second one is temperature. This is the Gibbs free energy equation. Gibbs free energy is equal to Gibbs free energy at standard state plus ideal gas constant with temperature by natural log of activity. So at activity is equal to 1, you could obtain the standard Gibbs free energy. From this standard Gibbs free energy, you could obtain the standard reduction potentials. And also, you can find some temperature term here. So basically, reduction potentials are the function of the temperature. Also, the standard reduction potential is the function of temperature. The temperature dependency of the standard reduction potential is not really strong, but anyway, that is the function of temperature. So you should recognize what kind of temperature is used for the standard reduction potential. In this table, there is some value and which is obtained at 25 Celsius degree. And let's go to the first point. The first point is about the reference electrode. The potential is not the absolute value. The potentials is always measured with respect to electrochemical reactions. Usually, hydrogen electrode is used as the reference electrode. These values are obtained versus standard hydrogen electrode. So, it is the reason the proton reduction reaction going into the hydrogen have 0 volt because the reference electrode used in this table is this reaction. Let me change the reference electrode from this hydrogen electrode to copper 2 plus copper electrode. Then the reduction potential of this electrochemistry is 0 volt. At the same time, the hydrogen electrode, the reduction potential is minus 0.34 volt. As a summary, there are 4 points are in this reduction potential table. The first one is the reduction. The reduction potential is based on the reduction. However, the oxidation potential is also have the same value. The second one, the standard reduction potentials are listed. It means this reduction potential at activity is equal to 1. Also 25 Celsius degree is the temperature at which the standard reduction potentials is measured. The number 4 point is we have used the standard hydrogen electrode. How to measure reduction potentials? In this case, I have used the standard hydrogen electrode as a reference, or SHE. Here are 2 compartments, and on the left compartment I have the standard hydrogen electrode. So let me check this hydrogen electrode. Hydrogen gas is introduced into the electrode surface. The pressure is 1 atm. So this is a kind of standard state. Hydrogen introduced into the surface of electrode is converted to proton via oxidation. The electrode is platinum. And also, the platinum is reduced on the surface of platinum into hydrogen gases. So, one more thing. The 1 molarity of nitric acid is used. So, the concentration of proton is 1 molarity. It is another standard state. Let me read the textbook. Text. The SHE is a piece of platinum foil. that is in contact with bubbles of hydrogen gas at 1 atm pressure and with H plus aqueous at 1 molarity concentration. So this electrode is called standard state or standard hydrogen electrode. Also on the other compartment I have copper 2 plus and copper 0. So maybe there would be some electrochemistry between copper 2 plus and copper. Those two compartments are connected to each other by using short bridge. And then I'd like to measure the open circuit potential between those two electrodes. Here is voltmeter, and the plus pole of voltmeter is connected to copper, and negative pole of voltmeter is connected to the reference electrode. And then I can read plus 0.34 volt on the display of voltmeter. And what is the reduction potential of copper versus standard hydrogen electrode? The potential difference of the previous cell is delta E. This is the reading value of voltmeter. Is equal to the potential, actually the reduction potential on the positive pole minus the reduction potential on the negative pole. So let me say the reduction potential on the negative pole is 0 volt because I have said we have the reference electrode on the negative pole. So the reduction potential of copper 2 plus copper is measured at plus 0.34 volt. Here is another example of how to measure reduction potential. Okay, the same thing. This is the standard hydrogen electrode, and on the left hand side of compartment we have zinc 2 plus zinc pair. And also in the same way the voltmeter is connected into the zinc on each positive pole, and then the negative pole of voltmeter is connected to the hydrogen electrode, and the reading value on the display of voltmeter was at minus 0.76 volt. And what is the reduction potential of the zinc 2 plus zinc? Of course, in the same way, the reduction potential of zinc 2 plus zinc is minus 0.76 volt versus standard hydrogen electrode. Cell potentials and free energy changes for cell reactions. We are thinking about the electrochemical cell. The first nomenclature related to electrochemical cell is electromotive force, shortly EMF. Actually, we have said about that in the previous chapter. The electromotive force is the driving force or electrical potential that pushes the negatively charged electrons away from negative electrode and pulls them toward the cathode or positive electrode. Never mind about the anode and cathode at this point. I'll show you them later. The electromotive force is also called the cell potential or the cell voltage. The cell voltage of galvanic cells is always positive. Never mind at this point. It is obtained by cell potential is equal to the potential of cathode minus the potential of anode. You know, the reduction potential is defined based on the reduction process, and cathode is the electrode of reduction. So usually the potential of cathode is considered as the positive, and then the potential of anode is considered as the negative. So plus electrode minus electrode is cell potential. I'll let you know about that later. Electrolytic cells. A cell that converts electrical energy into a non-spontaneous chemical reaction. So, you know, we have the second definition of electrochemistry, which is related to these electrolytic cells. No. The first definition of electrochemistry, the introduced in the chapter 1a, is related to electrolytic cells. At the chapter 1a, I gave you an example about electroplating of gold 2 plus onto the electrode. Then by applying some negative potential into the system, we have changed the gold 2 plus into gold 0. So this is the case, electrolytic cells. A cell that converts electric energy, it means we have applied some potential or electricity into a non-spontaneous chemical reaction. Okay, that is the electrolytic cells. So actually, we have two different cells. The first one is galvanic cells, which is based on the second definition of electrochemistry, and the second one is electrolytic cells. It's based on the first definition of electrochemistry shown in the chapter 1a. Still, we are on the cell potentials, and this is the very basic equation. Energy is the product of electric charge and electric potential. So E is equal to QV. Q is the electric charge. Its unit is Coulomb, and V is the electric potential in volt. And of course, the unit of energy is joule here. Okay, that's it. And I have said Q, the energy is equal to QV. The Gibbs free energy change of some electrochemical reaction is easily converted to the reduction potential or cell potential. So here is the cell potential, which is equal to V, and Q is going to minus NF. Why should we have minus sign? Because we are thinking about the electron and number of electron transfer in the reaction and Faraday constant. The meaning of Faraday constant is very important thing. The Faraday constant is Faraday constant is 96500 Coulomb per mole electron. The meaning of Faraday constant is the electric charge which 1 mole electrons have. So 1 mole electron is equal to 96500 Coulomb. So here is the number of electrons, and this is the Coulomb or electric charge of 1 mole electron. So the product of NF is going to some charge. So if you know the value of free energy change of some reaction, then you can calculate the cell potential. Also, at the standard state, the same equation is holding. So Gibbs free energy at standard state is equal to minus NF, the reduction potential at standard state, or the standard reduction potential. Okay, so here is some reactions, and the standard cell potential at 25 Celsius degree is 1.10 volt for the reaction. So this reaction includes two half cell reaction. Zinc is going to zinc 2 plus, and copper 2 plus is going to copper. So let me draw an electrochemical ordinate. So here is the electrochemical ordinate, and here's the plus sign, here's the minus sign, and then copper 2 plus copper reduction process. Copper 2 plus 2 copper metal is located at plus 0.34 volt. And how about zinc? Zinc 2 plus 0, zinc 2 plus zinc or zinc 2 plus 0 is at minus 0.76 volt. We could expect from this electrochemical ordinate, the electron is transferred from zinc pair to copper pair, right? So zinc would be oxidized, something like that, and then copper would be reduced by getting the electron from the zinc pair. So reduction happens, and then the cell potential would be read at about 1.1 volt. So maybe this one minus this one is 1.1 volt, or this one minus this is minus 1.1 volt. Anything is okay. So here is the question. Calculate the standard free energy change for this reaction at 25 Celsius degree. So delta G0 I means standard Gibbs free energy change is equal to minus NFE, and in this reaction we have two electrons are involved. Zinc is going to zinc 2 plus, so 2 electrons is generated, and 2 electron is moved to copper 2 plus, and finally which is going to copper. So minus 2 mole electron with Faraday constant 96500 coulomb per mole electron. Please memorize the number, the value of Faraday constant, but more importantly, please memorize the unit of Faraday constant, which is the coulomb per mole electron. Okay. Then what is the cell potential? 1.10 volt from the text. Or you can calculate like that from the standard reduction potential table at 25 Celsius degree. And then unit conversion. So finally we can obtain the value of Gibbs free energy change from the cell potential. What is the electrochemistry? Electrochemistry is the area of chemistry that deals with electron transfer, with the interconversion of chemical and electrical energy. Electrochemistry takes place at the electrode-electrolyte interface in an electrochemical cell. There are two different types of electrochemical cells. Okay, you can find very important keywords in electrochemistry in this text. So electrochemistry is the chemistry, of course, and electron transfer is another important keyword, and there are some interconversion between chemical energy and electrical energy. So this electrochemical reaction takes place at the electrode-electrolyte interface. This is another important point, and also which happens in an electrochemical cell. Electrochemical cells are a kind of tools and weapons we electrochemists are using. There are two different types of electrochemical cells. The first one is galvanic or sometimes voltaic cell. The other thing is electrolytic cell. The galvanic cell is a cell that converts chemical energy of a spontaneous chemical reaction into electrical energy. That is to say, from chemical energy to electrical energy. This galvanic cell is based on the second definition of electrochemistry introduced in my previous class. Thus, a spontaneous chemical reaction generates an electric current. On the other hand, here is an electrolytic cell. This cell that converts electrical energy into a chemical reaction. Again, electric energy into chemical energy. Thus, electric current drives non-spontaneous chemical reactions to occur. Let me get back to the slide for introduction of electrochemistry in my previous class, chapter 1a. I have taken this slide from the chapter 1a. So in this slide, I have said about the interconversion between chemical energy and electric energy. Also, I have two different electrochemical, two different definition of electrochemistry. The first one was chemistry controlled by electrons. Here is an example. By applying some electrons, we have changed the gold plus ions into gold metal. This is the electrolytic cell. Electrolytic cell. Electrolytic cell. Let's go to the second definition of electrochemistry. Electrons released by chemical reactions. For example, we could get some electricity from lithium-ion batteries during discharge process. So this second definition of electrochemistry is about galvanic cells. Galvanic cells. So you have learned about those two different cells already in the previous chapter 1a. Okay, here is an example of galvanic cells. Maybe you are very accustomed to this system. We have two compartments again here, and here is the zinc 2 plus, or zinc 2 plus zinc, and here copper 2 plus copper. So you have already know the reduction potential of zinc 2 plus and copper 2 plus. Zinc 2 plus is at minus 0.76 volt, and copper 2 plus copper at plus 0.34 volt. So the reduction potential of zinc 2 plus zinc is more negative than the reduction potential of copper 2 plus copper. So let me go back to the electrochemical ordinate here. So we have one pair of electrochemical species, and the other thing is the other pair of electrochemical species. We could expect the electron transfer from the more negative one to more positive one. In that case, zinc would donate electron into copper 2 plus, and at the same time zinc is going to zinc 2 plus and copper 2 plus is going to copper. We could expect by using the electrochemical ordinate with informed reduction potentials. So we could expect the electron is moved from here to there, and I'd like to emphasize this word, spontaneously. Spontaneously. Then we could get some electricity. This is the example of galvanic cell. Okay, so let me try to calculate the cell potential. Here is the full cell reaction. And this full cell reaction can be broken down to two half cell reactions. The first one is reduction, like copper 2 plus is going to copper. We know that. Also at the same time, we would have the oxidation. Zinc is oxidized into zinc 2 plus, donating electron into copper 2 plus. So we have two half cell reactions here, and the electrode of reduction is so-called cathode, and the electrode of oxidation is so-called anode. The cell potential is calculated from cathode minus anode, or in other words, reduction minus oxidation. So it's time to get some values about the reduction and oxidation process. So here is the values, and when you use the reduction potential value, please write down the chemical reaction equation as the reduction process. So the first one, reduction. Copper 2 plus 2 electron is going to copper at plus 0.34 volt versus standard hydrogen electrode. This is the same with this one, right? Let's go to oxidation part. So oxidation, of course, zinc is oxidized into zinc 2 plus. For describing the oxidation, this chemical reaction is right. However, I'd like to use the reduction potential. The reduction potential is based on the reduction process, so please write down the reduction process for the chemical reaction equation, even for oxidation reaction. So zinc 2 plus 2 electron is going to zinc metal. Okay, then I'd like to get the difference between those two reduction potentials. So this one minus this one, I have put the negative sign or minus sign on in front of the oxidation reaction, right? So I will subtract this one from this one. So you should place the minus sign is here. The first equation minus second equation. Then you can calculate the cell potential, which is cathode minus anode. 0.34 volt minus negative 0.76 volt. So you would have 1.10 volt. How about the chemical reaction equation? Here, copper 2 plus is going just down, and copper solid, copper metal, is going just down, and electron is removed by erasing this one and this one. Again, 2 electron minus 2 electron minus is going to 0, right? And the second chemical reaction equation for oxidation should be reversed after the minus operation. So zinc 2 plus on the left hand side of the equation is going to the right hand side of equation. Also zinc metal is going to the left hand side of the equation. So this is the full cell equation, like copper 2 plus here and zinc is here, is going to copper solid here, and zinc 2 plus aqueous is here. And each cell potential is measured at plus 1.10 volt. So the most important thing in this slide is that please write down reduction process even for the anode part for calculating reduction potential. After you operate the negative signs, then this position is reversed from here to there, and this one is from here to there. Okay, let me discuss more about the galvanic cells. In any cell, we would have anode and cathode, or oxidation electrode and reduction electrode. But anyway, at the first time, I'd like to introduce anode in galvanic cells. What is the anode? Anode is the electrode where oxidation occurs. That is to say, cathode is the electrode where reduction occurs. So here is the memorization tip. Oxidation starts with Bauer, R-A-E-O-U, and anode also starts with Bauer. Let me write down Bauer. Bauer. So Bauer corresponds to Bauer. So anode is for oxidation. Let me think about cathode. Cathode. Cathode is for reduction, right? Reduction. So reduction starts with consonant. Consonant. In Korean, jaum. Consonant. And also C starts with the consonant. This is S. C-O-N-S-O-N-E-N-T. Consonant. So you can match consonant with consonant. So cathode is for reduction. This is a kind of memorization tip. Let's go back to anode. Also, the anode is the electrode where electrons are produced. Here is the zinc metal, and zinc is oxidized into zinc plus, so electrons are generated via oxidation. At the same time, anions is approaching to the anode because we have extra positive charges here, because electron is going out of the electrode and we are producing zinc 2 plus into electrolyte. So we have some positive attraction, so negative ions or anions is approaching to this electrode anode. So how we have named this electrode as anode, because this electrode is the electrode which anions migrate toward. Anions is going to anode. Okay, so this is anode. Actually, Faraday named this electrode as anode. Okay, so in the galvanic cells, anode has a negative sign because electron is produced, so this is negative. But anode is not always a negative sign. Actually, in electrolytic cells, anode has a positive sign. So don't match the anode with negative, depending on the situation. But anode is always for the oxidation. Okay, let me go to the cathode, which is the electrode where reduction occurs. Again, consonant with consonant. So cathode is matched with reduction, and electrons are consumed, and cations migrate toward the cathode. So the name of cathode is coming from the cations. In galvanic cells, cathode has a positive sign, but in electrolytic cells, cathode has a negative sign. Again, back to these chemical reaction equations, and we have copper zinc pair for generating electricity. There is some note. The IUPAC, International Union of Pure and Applied Chemistry, strongly recommend that the terms anode and cathode be used to avoid confusion. It is therefore strongly recommended not to use term like left and right electrodes. I hate them. As well as negative and positive electrodes, unless you know what they mean for sure. So, negative and positive electrodes are very useful for battery systems. However, I have said that the anode is not always negative electrode. Cathode is not always positive. So depending on your cells, sometimes electrolytic cells, sometimes galvanic cells. So depending on which kind of cells you have, the sign of the cathode and anode is determined. You should be very careful about that. Shorthand notation for galvanic cells and the same cell, and here is the notation. So on the left side you should replace anode part, and on the right side you should have cathode half cell part. So this is the electrode, zinc, solid metal. And then in the electrolyte to the zinc electrode, we have zinc 2 plus. This vertical line indicates phase boundary because this is solid and this is the liquid. Let's go to the right side, copper and copper 2 plus. Of course, zinc is going to zinc 2 plus and copper 2 plus is zinc to the copper in the galvanic cells. So from left to the right. Between those two compartments, we have double vertical lines, which indicates salt bridge or separator membrane. Zinc would generate some electrons and then it is going along the external wire, then finally reach to the copper. So electron flows also from left to the right. This is the shorthand notation for galvanic cells. Okay, again back to cell potential calculation. You did it, right? So again, please write down the chemical reaction equation as the reduction process when you write down the reduction potential, because reduction potential was defined based on the reduction process. Copper 2 plus electron is copper, reduction. Zinc 2 plus 2 electron is going to zinc. Even if the second equation is for the anode process or oxidation process. But for writing down the reduction potential, please place the reduction process. However, you should write down cathode and anode or reduction and oxidation. The reduction process or cathode process should be located at the first row, and then in the second row you should place the anode part, because the cell potential is calculated from cathode minus anode or reduction minus oxidation. Then minus, you could have the cell potential, and also you could obtain the full cell chemical equation. Let's go to the more difficult example. We have silver plus silver pair, also copper 2 plus copper pair. If you know the reduction potential, actually standard reduction potential versus standard hydrogen electrode for the corresponding chemical reaction equations, then you could expect which one is cathode and which one is anode for galvanic cells. The reduction potential of silver plus silver is plus 0.80 volt, and copper 2 plus copper is at 0.34 volt. So the silver guys is more positive than the copper guy. So maybe the more positive guys would donate their own. No. More positive guys would accept the electrons from more negative guys, right? So silver plus silver pair is on the cathode, and copper 2 plus copper pair on the anode, and then minus sign. So let me obtain the full cell equation first. You should compare the number of electrons. For the first reaction, we have only 1 electron. However, in the second reaction, we have 2 electrons. So to remove electrons to obtain the full cell equation, you should multiply the first equation by factor 2. Then 2 silver plus is going to there, 2 silver solid is going to there, and then 2 electron minus 2 electron is going to 0. Copper 2 plus is going to the right hand side of the equation, and copper matter is going to the left side of the equation. Then that is the full cell equation. Good. And then it is time to calculate the potential difference between those two reactions. We have the multiplier, which is 2 here. Then some of you guys would calculate in this way. 2 by 0.80 is going to 1.6 minus 0.34 volt. So the answer, or the cell potential, is 1.26 volt. Is it right? Definitely wrong. So let me think about the water molecule here. Here is one water molecule, so oxygen and hydrogen there. And the boiling point of this water molecule is 100 Celsius degree. And right now, I'd like to add one more guy, 2 water molecules. Then is the boiling point 200 Celsius degree? No. The boiling point is the intensive properties. Intensive properties. So the value is not depending on the amount of molecules. The same situation for the reduction potential. Reduction potential is intensive property. So you cannot multiply this reduction potential by the factor 2. Just 0.80 minus 0.34 volt is the answer of the cell potential. So my answer is plus 0.46 volt for these reactions. How to balance redox reactions? Here are rules of balancing redox reactions. I'd like to check just the first rule here, but please read the rules 1, 2, 3, 4, 5. The rule number 1, obtain the oxidation number or the valence state of an atom undergoing a change in its valence state in a compound or an ion. The valence state of any atoms in their elemental state is always 0. For example, hydrogen gas, H2. H atom in hydrogen gas is 0 as its oxidation number. The sum of valences of all atoms in compound must be 0, of course, neutral atoms, while it is the same as the charge for an ion, of course. In compounds, the oxygen and hydrogen atoms usually have valences of -2 for oxygen and +1 hydrogen atoms. So the first choice of what you should determine its oxidation number is hydrogen and also oxygen. Don't forget it. Hydrogen and then oxygen. +1 and then -2. Let's go to the example. Here is examples about the oxidation number of various molecules, atoms, or compounds. Atoms in elemental state, for example, sodium, hydrogen molecule, bromine, and carbon. All atoms have 0 as their own oxidation number. Okay, how about ions? Sodium plus have the plus 1 as its oxidation number, calcium 2 plus, 2 plus, 3 plus, minus, 2 minus, of course. Okay, here is more difficulty, more complicated situations. We have the compound here, and most of them are oxide. So nitrogen oxide, sulfur oxide, phosphor oxide, and chlorine oxide. So how can we determine the oxidation number of each atom? I have said the first choice should be proton and then oxygen. So in this case, oxygen. So oxygen should have, oops, wait a moment, red. So oxygen should have 2 minus. So we have 3 oxygen atom in NO3 minus, so totally 6 minus is developed by oxygen atoms. So to give us the total number of electrons is 1, then the nitrogen should have the 5 plus. So the oxidation number of nitrogen in NO3 minus is 5 plus. Okay, let's go to the other half-cell reactions. Half-cell reactions, and here is the mangan pair, chromium pair, sulfur pair, and chlorine pair. So let's do the balancing for the first case. Okay, right now we have 2 pairs, so let me say the chemical reaction equation is following as manganese oxide MnO4 minus is going to Mn2 plus. And on the right hand side of the equation, we don't have any oxygen species, so plus oxygen molecules. And then it's time to determine the stoichiometric coefficient of each entity of the equation. So one mangan, so just 1, and 4 atoms of oxygen, and we need to have 4 atoms of oxygen on the right side, so 2 oxygen molecules. And then let me check the charge. We have -1 on the left hand side of the equation. However, we have 2 plus on the right hand side of the equation. So you should add 3 electrons on the right hand side. Then totally -1 is equal to -1. That's it for balancing half-cell reactions. Let's go to full-cell reaction for balancing redox reactions. Here, last carbon, Fe2O3 carbon, is going to Fe matter and then CO2. So let me check the oxidation number. Oxygen should have 2 minus, but 3 atoms of oxygen, so it is going to 6 minus, and then totally Fe should have 6 plus. So here is 2 Fe atoms in Fe2O3, so the oxidation number of Fe atom is plus 3. How about the Fe matter on the right hand side of the equation? Of course 0. This is just the element, so 0. So the difference of oxidation number in Fe is -3. 0 minus +3 is -3. Let's go to the carbon. Carbon element 0, and how about carbon dioxide? 2 minus here, so totally 4 minus from oxygen, and then carbon should have 4 plus, and this is just 1 carbon, so oxidation number of carbon is +4. 0 to +4, so the difference in oxidation number is 4 minus 0 is going to +4. And then we should balance between the electron gain and electron loss. It means balance between reduction and oxidation. So I'd like to multiply the number -3 by factor 4. And also here we have +4, so we should multiply this one by the factor 3. So 4 Fe atoms is required on both sides of reaction, and also 3 atoms of carbon should be there on both sides of chemical equations. Okay, so for Fe, so right now we have just 2 Fe, so 2 here and 4 here. How about oxygen? How about carbon? 3 and 3. So that's it for balancing full cell reactions. Here is the several more examples of redox reactions, and please balance the following net ionic equation in acidic solutions. 1, 2, 3. Please do the balancing by yourself. The Nernst equation. The Nernst equation is the most important part of the thermodynamics for electrochemistry. Also, this sub-item is the last item of this chapter 1b. So, this is the Nernst equation. The Nernst equation, this is the Nernst equation. The Nernst equation starts from the basic thermodynamic equation like delta G, the Gibbs free energy change of reaction, or the Gibbs free energy of some change is equal to the Gibbs free energy at the standard state plus RT ln quotient. Quotient means the ratio of the concentration or activity of products per activity or concentration of reactants. Then, using the relationship between Gibbs free energy and electric potential, then we could obtain the Nernst equation like that. This Nernst equation is obtained for this reaction. Oxidized species plus n, number of electron transfer with electron, is going to reduce the species. For example, copper 2 plus is oxidized species plus 2 electron is going to reduce the species, in this case kappa 0, something like that. And then finally we have the final form of Nernst equation. E is equal to standard reduction potential minus RT and F natural log with reduced species per oxidized species. At room temperature, some value is obtained here with common log, like 60 millivolt here. Anyway, usually we will use this one. Oh, I forgot something. Okay, let's go forward. So, let me apply the Nernst equation for half-cell reactions into several examples. Fe3 plus is going to Fe2 plus. So, here is the standard reduction potential. Then, that is the plus 0.77 volt, which could be read from the table of the standard reduction potential at usually 25 Celsius degree. And let's go to the log. So the product per the reactant or reduced species per oxidized species. So Fe2 plus is there, Fe3 plus is there. Okay. Let's go to copper 2 plus is going to copper. The reduction potential is equal to 0.34 volt. That is the standard reduction potential. Minus RT NF Ln, reduced species, it should be copper, the concentration of copper. But the concentration or activity of solid materials is considered as just one. Always. Remember? The one for solid material. And then let's go to the denominator, kappa 2 plus reactant. So kappa 2 plus. So 1 over kappa 2 plus. Example number 3. So some manganese species here, and then the 1.5 standard reduction potential would be calculated from or read from the table, and then reduced species or the the product, and then it should be Mn2 plus with H2O to the 4. However, this is the solvent molecules. We have a lot of water molecules in this chamber, in the beaker, so it could be considered as one like solid materials in the above example. The other thing is Mn2 plus on the reactant, and on the denominator MnO4 minus and H plus to the 8. H plus to the 8. Of course, n is equal to 5. Let's go to the example 4. This equation, and then n is equal to 2. Reduced species is OH minus square because its stoichiometric coefficient is 2. And of course, you should have Mn2O3 next to the OH to the 2. However, this is solid, then the activity of the solid material is considered as just 1. The other thing is MnO2, but this is solid, so just 1. And H2O, solvent molecules, and also liquid is 1. So the final, the Nernst equation is like that, ln just OH minus a square with, here is the 2. Also, the same Nernst equation could be applied to full cell reactions. Actually, everything is the same. Then here is the example about the full cell problems. So copper is going to copper 2 plus oxidation, and the Fe3 plus is reduced into Fe2 plus. That is the full cell reaction, which have two different half cell reactions. The question is, what is the potential of a cell at 25 Celsius degree that has the following ion concentration? Fe3 plus, not 1 molarity but 10 to the minus 4 molarity. Copper 2 plus, not 1 molarity but 0.25 molarity. Fe2 plus, not 1 molarity but 0.2 molarity. That is to say, the standard reduction potential is not enough for the calculation. You know, the standard reduction potential is defined at the activities or concentrations are equal to number 1. However, we have some concentration which is very different from 1 molarity. So we should think about the effect of concentration in log scale. So let me calculate it. The first thing we want to calculate is standard reduction potential. That is the starting point. So this full cell reaction is divided into two reactions, half cell reactions, Fe3 plus to Fe2 plus. Then you can read the standard reduction potential in some tables, plus 0.7 volt. And copper 2 plus 2 electron, as you know, plus 0.34 volt. The reduction potential of the first equation is more positive than the second equation. So reduction happens on this reaction, half cell reaction, right? And oxidation. So cathode, anode, and minus. Finally, we have 0.77 minus 0.34 volt. It's going to 0.43 volt. That is the cell potential at standard state, or standard cell potential. Okay. Now right now we have the value about this red guy, and then it's time to calculate the concentration term or quotient. This equation is here, and E0 we have 0.43 volt by our calculation, and number of electron transfer is 2. Kappa is going to kappa 2 plus 2 electrons transferred. Also, 2 ions of Fe3 plus is going to 2 ions of Fe2 plus. So 2 electrons are moved. Then n is equal to 2, going to 2. And put the concentration into the each concentration term, something like that. And then finally we obtain the reduction potential. The standard reduction potential was 0.43 volt, but right now, after changing the concentration from 1 molarity to some specific values, the reduction potential is going to plus 0.25 volt. So I means the effect of concentration is very significant to determine during determining the reduction potential of full cell or half cell reactions. This full cell potential is an equilibrium potential, which is also an open circuit potential. Okay, we are still on the same equation, same the electrochemical reaction equations: kappa 2 plus, Fe3 plus, Fe2 plus. So we have applied the Nernst equation into this full cell equation. Then we have calculated the final cell potential, full cell potential. But by using the half cell reactions, also we could calculate the final answer. Okay, so let me do it. I have applied the same Nernst equation to half cell reactions about copper and also about Fe species. Then the half cell potential was obtained. So that was the plus 0.32 volt for kappa 2 plus 0, and the Fe3 plus 2 3 plus 2 plus electrochemistry have plus 0.57 volt as its reduction potential. So let me think about that. Let me compare the standard reduction potential and the final reduction potential, which would be affected by the concentration. So here, oxidized species plus electron is going to reduce the species. In the case of kappa 2 plus 0, it would be kappa 2 plus 2 electron is going to kappa 0, right? And if you have 1 molarity of reduced species kappa 0, actually always kappa 0 is going to 1 molarity. And also, if we have 1 molarity of kappa 2 plus, then we could obtain the standard reduction potential for this half cell reaction, right? However, no. Actually, the standard reduction potential is obtained at 1 molarity of reduced species and 1 molarity of oxidized species. More generally, if you have the same concentration of activity for both reduced species and oxidized species, also this term is going to 0, then the reduction potential is equal to the standard reduction potential. However, in this situation, we have 0.25 molarity, which is much smaller than the 1 molarity. But kappa 0 is at 1 molarity. So the equilibrium is moved from the right side of this equation to the left side, like in Le Chatelier principle. So oxidation reaction is favored, then the reduction potential is going to more negative values. I have said more negative reduction potential indicates oxidation is favored, right? So again, by the Chatelier principle, the backward reaction, actually oxidation reaction, is favored, so the reduction potential is going to the more negative values. Let's go to Fe side. Here is the reduced species. Okay, let me write down the species. Fe2 plus and Fe3 plus. So right? So I have said we would have standard reduction potential when the amount of oxidized species and reduced species are the same. However, in this case, the amount of oxidized species is much smaller than the amount of reduced species. So, backward reaction is favored by Le Chatelier principle. Then oxidation is favored, therefore the reduction potential is going to negative potential. Then the final potential gap between those two reduction potential is going to the answer about the full cell potential. That is the last slide of the chapter 1b. That's it for the basics of electrochemistry.